I welcome you to CS Katha Barta, where we invite academics and professionals to deliver their talks. The guest for today is Dr. Adarsh Barik. He is an assistant professor in Department of Computer Science and Engineering at IIT Delhi. Before joining IIT Delhi, he was a research fellow in Institute of Data Science at National University of Singapore. He obtained his PhD from Department of Computer Science at Purdue University. Um, and before that, he did his BTech and MTech from IIT Madras. His research interests are broadly in theoretical and computational aspects of optimization, machine learning, information theory, and high dimensional statistics. Today, he's going to speak about sequential decision making under uncertainty. I welcome you, Dr. Barik, to CS Kathavarta, and I request you to start your talk. Thank you.
Yes, thanks for the kind introduction, Rucha. Right. So I'll start the talk, and again, I cannot see any one of you. So if you have any question, you can just shout out, and we can discuss then. All right. So today I'll be talking about sequential decision making under uncertainty. In particular, we'll be focusing on parameter-free algorithms in something called stochastically extended adversarial model. Now, some of these words, some of these terms, they might be unfamiliar to you, but as we move along with the presentation, we'll discuss these more formally. As Rucha told, I'm Adarsh, and I'm an assistant professor in computer science department here in IIT Delhi. Now, this work was done when I was a postdoc at National University of Singapore. This is a joint work with a PhD student Shu Che Wang and Professor Peng Zhao and Professor Vincent Tan. All right, let's move ahead. So I'll start with listing down the objectives of this talk, right? So at the end of the talk, you should be familiar with sequential decision-making problems under uncertainty, and especially within a framework called online convex optimization. I'll try to make a case for the need of parameter-free algorithms, and I hope that you appreciate that we do need these sort of algorithms in practice. And then we'll focus some of our times in a framework called stochastically extended adversarial model. Initially, I'll start with some motivating examples, and as we move along, as we see more results and more bounds, things might get a little bit dense in terms of math. But I would suggest that you focus on big ideas in this talk. Math will follow automatically, and if you don't understand anything, you can always go back and read the paper anyway. So the focus, it will be nice to have the focus on big ideas, and it will be easier for you to follow the presentation that way. If you have any question, you can just ask, just shout out, and then we can discuss the question. Right. So let me start with this simple question. So I am considering whether I should carry an umbrella tomorrow or not. Now, there might be two scenarios here, right? So I asked this question to myself, that should I carry an umbrella tomorrow? And I might decide no. But the thing is, what if it rains tomorrow, right? Now I can't do anything about tomorrow since I decided to not carry the umbrella. If it rains, then it rains. But I can make a better informed decision for day after tomorrow. Maybe day after tomorrow, I'll start keeping umbrella with me, right? So this is pretty much the pattern for sequential decision making under uncertainty. The main thing to learn here would be I'm taking a decision for tomorrow without knowing the future. And once I get the feedback about the future, then for the next iteration, I might change my decision. So based on the feedback I'm receiving for my actions now, I'll change my actions later on. So that is basically the pattern of sequential decision making under uncertainty, and we'll see more examples of this. Now, there might be slight modification of this scenario. There might be another scenario where rather than just taking a decision, I might ask someone. So I might ask you, like, what do you guys think? Should I keep an umbrella with me tomorrow? And you might say that no need, since you know that it has not rained since say last 1 month, or it didn't rain today, then probably it won't rain tomorrow. And I trust you. I say, all right, I won't keep the umbrella. But if it actually rains tomorrow, then I'll change my decision later on. So here I'm taking help from you. I'm trying to, so I'm making the decision, but there is this involvement of some sort of knowledge about future, which I expect you to have, right? This knowledge might not be great. So you might say that it did not rain today, so it might not rain tomorrow, but that might not always happen. So you're trying to guess the future. You're trying to provide me some hint about the future, but that hint might be good or bad depending on the situation. Now, this sort of scenario is called optimistic sequential decision making, where I have optimism about the future because I'm trusting your judgment about the future. So we'll discuss these two scenarios more formally later on, but you keep in mind these two examples, these two scenarios about taking decisions about future, right? One without hint and one with hints.
Just a quick query.
Yeah.
So, like optimistic in the sense, like it's specifically you said, like it has to be a positive or it can be negative as well.
No, it can be negative as well. Yeah.
Okay.
Yeah. So whatever we'll discuss, we'll discuss some sort of bounds on our performance. Those performance bounds would depend on whether it is whether your prediction is accurate or not. So if you have a bad prediction or bad guess about the future, then your bound would be bad. But if you happen to have good guess about the future, then the bound would be better.
Okay.
Right. So this we'll come back to these scenarios over and over again, and we'll see some examples as well as we move along.
There is one more. Sorry, there is one
yeah.
more query. Like, so this is Bayesian.
Right. So here we are not assuming any prior information or anything like that. So let's talk about a completely adversarial setting, right? Where the future is governed by some adversary and they can make our life as difficult as possible. So we are trying to play a game against some adversary who is controlling the future. We'll talk about some stochastic things later on when we discuss the stochastically extended adversarial model. But before that, we'll assume that everything is adversarial. There is some adversary sitting somewhere who is governing the future.
Thank you. Yeah.
All right. So let's take a better motivating example, maybe. So now this guy comes to you and this guy asks for help about what you say. So they have this, so they want to spend some money in stock market, right? And they have this multiple options. They have Apple, they have stock of Google, Meta, and Nvidia. And they want to distribute their wealth among these four options. And they come to you and they ask, what is a good investment strategy? Now, you tell them this is a vague question. Like, what do you mean by a good investment strategy? What is the measure of goodness? And they come back to you and they tell you that if they earn profit from the market, then it's a good investment strategy. If they don't earn the profit, then maybe it's not a good investment strategy, right? But you say again that even this is vague, right? Suppose a market is giving return. So suppose you invest $1 in the market and you get return as $100. So people are expecting a lot of profit from the market. And in that situation, if this guy invests $1 and gets back $50, they are earning some profit, but maybe that's not a good investment strategy. So you again ask them to define this more properly, like what's a good investment strategy. Then they come up with this idea saying that, okay, what I want is I want to do better than someone else. So better than a competitor. And how do they define the competitor? So their competitor is defined as this person who will call lazy, annoying, know-it-all. So I'll explain why I'm calling them lazy, annoying, know-it-all. So we'll start with know-it-all. So this know-it-all guy, this guy knows the future. So for example, you want to invest your money for 1 year, but you don't know which of the stock option would perform better after 1 year, right? But this know-it-all guy knows that. So for example, they know that Meta would perform really well and Google will not perform well in next 1 year. They are lazy because they employ this strategy that they put all their money in Meta because they know that after 1 year, Meta would be performing really well. They put all their money in Meta and they just sit down and relax. Annoying because nobody likes know-it-all people, right? So that's the competitor. That's the baseline that we are competing against. And now they are asking, what's a good investment strategy? A naive way to do this would be to put all your money in one of the stock options. So for example, you might think that Meta will perform well and you put all your money in Meta and that will work out for you. But you might guess that Google will perform better in next 1 year and you put all your money in Google and that might not work well for you in next 1 year, right? A better strategy in this scenario would be invest in steps. So what you do is you pick a distribution. For example, you say divide your money in 4 parts, and you invest one part in Apple, one part in Google, one in Meta, and one in Nvidia. Now you wait for 1 month. After 1 month, you observe market response, right? And once you get this feedback, this market response, then you change your distribution. So suppose after 1 month, Meta performs better than Apple, then you take out some money from Apple and you put that money in the Meta. So you do it iteratively. And now with this strategy, you hope that at the end of, say, 1 year, you'll perform as well as this lazy, annoying, know-it-all guy. And the question is, does something like this work in practice? So let's try to understand some of the terms here that we are using. So you are taking a decision here, and this decision could be to invest in Meta, right, at certain month. And now you are getting a feedback based on your decision. The important part here is you are taking the decision first, then you are getting the feedback. And this feedback would be you have bad return in 1 month. Who is providing this feedback? Some environment is providing this feedback. In this case, it is the market, right? So market is providing you feedback, and based on the feedback from market, you're trying to change your decision. So these are the terms: decision, feedback, environment. We'll be using this over and over again. So we will try to map these terms to our examples. So this is one example where sequential decision making under uncertainty comes into the picture, where you want to make some decision, but you don't know anything about the future. So you do it sequentially and hope that in the long run, you'll do as good as, say, some baseline, which we have defined already. And this seems like a synthetic example, a constructed example, right? But this sort of problems appear everywhere in real world. We'll see some examples of them. So let's talk about this example where you're trying to make policy during the coronavirus pandemic. So we all went through this pandemic, right? And all the governments all over the world, they were trying to develop some sort of policy to deal with this COVID pandemic. Now, how do you develop these policies? So you take some decisions. Suppose you say that mask is mandatory for everyone in next 1 month. Then in this next 1 month, you try to get some feedback by conducting some surveys. And once you get the feedback, you decide whether after that 1 month, whether mask mandate is necessary or not, right? So government policy making can be modeled as sequential decision making problem. Here, the decision is whether to have mask mandate or not. Feedback could be new cases, or what is the infection rate, or what is the death rate, and things like that, right? And environment in this case is population at large, because you are conducting a survey across some population. So again, this sort of problem it appears a lot in real world, and this can be modeled as sequential decision making problem. Let's go to some other domain. Let's talk about traffic routing, for example. So where you will have to decide in real time whether you want to take a particular route or not. So decision in this case would be taking route X. Now, what is the feedback that you get after taking a decision? The feedback you get is what is the congestion in this route, right? And who provides this feedback? The traffic system, the Google map maybe. And this congestion depends on, say, other parameters like what other vehicles are opting for the same route and things like that. But once you know about this congestion data, once you have this feedback, you might decide to change the route or follow the same route depending upon the situation, right? So again, traffic routing can be modeled as sequential decision making problem. In fact, Google Maps, at least a few years back, they used to have this. They used to model this problem as online convex optimization problem, which we'll see in this talk. Right. Another example from another domain. So in this example, you want to detect spam, and this could be, say, spam in email, or spam in, say, you have some music app, and in this music app, you want to detect whether some music is from AI generated slop or whether it's a genuine music, right? That's a decision that you want to make here, is whether the content is spam or not. What is the feedback here? So whatever spam filter that you have, it might say that this particular content is, say, spam, but user has to provide you feedback. User decides whether this is spam or not. User might say that the content that you are saying is spam is not actually a spam. So the feedback is user's response, and environment in this case is user. So again, three completely different examples from different domain, but each problem can be modeled as a sequential decision-making problem, where we are taking a decision, waiting for the feedback, and changing our decision based on the feedback. Right. So this is the setup. You have learner takes a decision goes to the environment. And we talked about this, that environment could be completely adversarial. So they can provide you a very bad feedback. But let's not assume that they are completely adversarial. They can also be nice, right? You can get some good feedback that can actually help you learn something. But this is the setup that we have in this talk. And then you play this game iteratively, sequentially. Right. So we'll be putting two requirements, which seem natural to me, but let's just go through those requirements. So we'll model functions, right? So if you take a good decision, then that should lead to a small loss function. That seems quite natural, right? If you make good decision, then you should see a small loss function. If you make bad decision, go away from the good decisions, then you should see large loss. The second thing requirement that we'll put in this formulation is we'll assume that we can interpolate actions. Meaning you can take a bad action and you can take a good action. And we'll assume that you should be able to take all, say, moderately good or bad decision between those two endpoints. So you can cover all the spectrum. Now, this is not always possible. Sometimes decisions are discrete, but we'll assume that that's not the case in the way we are modeling.
Just a quick one.
Yeah.
So here, like the good decision should lead to a small loss. So we are assuming that every iteration will lead to the goal, right? So as in, it's not like a long-term goal that the K-hop actions will be finally good, where in between might give us some loss. It's not that way. The setup currently is like every step towards the goal has to give some positive feedback.
No. That's not the goal. So you take the decision and you get a feedback. And this feedback that you get could be large. So it could be large loss or it could be small loss. So that's not under your control. But you are saying that at the end of this game, say after playing for capital T number of rounds, whatever way you perform, it could be a large, you can accumulate a large loss, right? But this large loss would be comparable to some baseline. So if you perform badly, then the baseline will also perform badly.
So here, like after how many decisions are you comparing? Like, is there a like, or it's like a single decision that there is a comparing?
No.
Okay.
So we'll be comparing after, say, capital T number of decisions, some time horizon.
Okay. Okay.
So in the next few slides, we'll actually formally define what is our performance measure, and I think it will be more clear after that.
Yeah, I was basically because every decision will give some feedback. So the decision can be for you, it's like a T number of decisions, right? Yeah. Okay.
Yes, but the problem here is since the feedback could be adversarial, right? So for an example where whatever I do, the adversary says that it's a bad thing to do. Now I incur large amount of loss over, say, T number of rounds. But I'm saying that if I incur large amount of loss, then any baseline you pick will also incur large loss, so that my loss is comparable to some baseline.
Okay, and this particular system, like setup, like assumes the environment to be adversarial. Like, can it be the other way around also? Like, what if it's like a positive environment? Like, it always gives you good feedback. Then also it's okay, right?
Yeah. So we'll start with seeing some bounds for the completely adversarial case. Then we'll cover some scenario when things are not completely adversarial, and we'll define what do I mean by not being completely adversarial, and then we'll see some bounds for that as well.
Okay.
Right. So now let me introduce you to the framework of online convex optimization. So again, the same setup, learner is taking some decision, but now decisions are coming from a set, convex set, right? That we are calling convex set. The decisions will go to environment, and then we'll get some feedback, which we are modeling as loss, but these losses are not now convex losses. Now, I assume that most of you would know what a convex set and what a convex function is, but we'll just spend a couple of minutes to see them in very high level, right? I won't go into detail about this thing. So one example of modeling the loss would be, say, this function theta minus theta star. You take the norm and square it. So here it's clear that theta star is a good decision. So when you play this decision theta star, then your loss would be 0. But as you go away from this theta star, then your loss starts increasing. And if you actually plot this guy, so suppose you go away from theta star, which is not so good decision, then you have this higher loss. And if you plot it in one dimension, at least it looks something like this. So these sort of functions are called convex function at very high level. When I say convex losses, you can assume that these are easy to minimize. If the loss is not convex, then it might be difficult to minimize. So non-convex losses are not easy to handle. A more formal definition would be if you draw a tangent from any point in the convex loss, then the entire function would lie above the tangent. But don't worry about the technicalities here. Just assume at this point of time that convex losses are easier to deal with. That's why we are modeling the loss functions as convex losses. Now, what is convex set? So the convex set says that if there are two decisions, say θ1 and θ2, which are inside the set, then any decision between those two. So if you join θ1, θ2 by a line segment, this entire line segment will lie inside the set, right? So we talked about this requirement that if you take a good decision and bad decision, then you should be able to take all the decision in between, right? So this is somehow modeling that sort of requirement. That if I can take θ1 and θ2, then I should be able to take all the convex combination between θ1 and θ2. So this is the set that we are picking our decisions from. Right. So let's talk about performance measures. So we already discussed this somewhat, but let's make that more formal. So we are trying to compare our performance against a fixed baseline. So we'll define a quantity that we'll call regret. And this takes the argument some sort of baseline U. So this regret has two terms. The first term will collect all the losses that we see as a learner. So at every round t, we are seeing ft theta t based on our decision theta t. This is the loss we are seeing. So we'll sum it up across round from t is equal to 1 to capital T, right? And then we'll subtract this loss of the baseline. So the baseline will pick a single decision U across all the rounds, and whatever loss that they incur by that single decision, that would be the loss for the baseline, and we'll subtract our loss. We'll subtract the baseline's loss from our loss, and that would give us regret. U could be any decisions, right? So in most of the scenario, people pick U to be decision that minimizes the second term, which is fine. Our guarantees would hold for any choice of U. So this is the performance measures which we'll call regret. Is there any question now?
Nothing yet from the audience here.
Yeah. So now let's move ahead. So the immediate question would be, can we control this regret? And turns out yes. Most of you would know gradient descent. An online version of gradient descent works pretty well for this problem. So we'll call the algorithm online gradient descent algorithm. Now we'll need to know a bit about the setup. In this setup, I'm assuming that the convex set that I'm picking the decisions from is bounded, is compact, so it has a diameter, a finite diameter capital D, right? Algorithm is pretty similar to the gradient descent algorithm. So we are playing this decision theta t from that convex set, and then we receive this first order feedback. So we receive gradient information and the function value information. The function value information is not needed, but for now we'll just keep both the information here. So we are just receiving first order feedback, just the gradient information, nothing more than that. Now for the next round, we'll update our decision theta t plus 1 by just making a gradient descent update. So we'll take the negative gradient direction and move in that negative gradient direction by some step size eta. Eta is also called learning rate. Now this movement might take us away from the convex set capital theta. So we'll need to project it back to this convex set. So we are taking a projection after making this movement. This is very similar to gradient descent in offline case. So we'll call it online gradient descent, and this works pretty well. So this algorithm would give you a regret, a bound on the regret U, which depends on some quantities. Let's see those quantities. So the bound depends on diameter. So it has d square dependency on diameter, d square by 2 eta. Eta is the learning rate. And the second term is basically summation of this norm of the feedback that we are receiving, a norm of the gradient of the feedback that we are receiving. And then eta is in numerator here. Now, once you see this formula, you can notice that we can pick eta very carefully, so to minimize this right hand side. So the next step would be how do you pick this learning rate, and learning will pick a learning rate which minimizes the right hand side, right? So if we do that, is there a question?
Just a quick, the projection that was done to make sure the diameter remains within D is
Yeah.
the okay.
This is pi theta is the projection.
That was done to make sure the next decision is within the diameter D.
Within that set, convex set, yeah, of diameter D. Yes.
Okay.
Yes. Right. So next thing to do here would be how do you pick this learning rate, and we'll pick a learning rate that minimizes this right hand side quantity to get a good bound on the regret, right? So if you set this learning rate eta to be D divided by square root of this summation of T is equal to 1 to capital T, norm of gradient of 50 theta T square, then this leads to a regret which is order of D times this square root of this summation of all the norm of the gradient square, right, inside the square root. If each of these quantity, each of the norm of gradient is bounded, then you get order square of T regret bound. And this is the best you can do. So you can always show, you can also show that for convex problems, the lower bound is also of the order square root of T. So this is the tightest bound that you can get. Why is this a good bound? So if this is a good bound because if you take, say, average regret, meaning you take the regret and then take average across capital T round, so 1 by T of the regret U, then that is order of 1 by square root of T. And as you increase T, this vanishes. So average regret vanishes as you increase T. So this is a pretty good bound using just a simple online gradient descent update. But now, can you identify some problem with this setup or this result? So one of the problems that you'll quickly notice is the recommendation of learning rate takes into the consideration of all the gradients information, right? From T is equal to 1 to capital T. Now we are playing this game sequentially. So suppose you are at iteration number 1. So you don't know anything about the future. So you cannot compute this summation because since you have not seen all the gradients, so you cannot have this summation. So you can't compute this. So you can't actually compute this recommended learning rate without observing all the rounds, right? So again, this is a good result, pretty tight result as well, but it's not possible to do in practice. The second thing would be, what about the domain diameter, right? So there might be two things here. One, the diameter might not be known to you while playing the game. The second thing could be diameter could be large. It could be unbounded. If diameter is unbounded, then your entire this regret bound becomes vacuous because it depends on D, right? If D is large, then this bound is kind of vacuous. So this tells us that, yes, this result is good, but we still need to do something more. And this motivates us to develop parameter-free algorithms. So algorithms which are adaptive to the domain. So once if you don't have the knowledge of D, then how do you have good regret bounds? So we need to develop algorithms like that. We also need this extra requirement that whatever parameter that you pick, whatever say learning rate that you pick for those algorithms, they should only depend on the quantities that you have seen already. So if you don't have any information about certain quantity, then your learning rate should not depend on those quantities. So this motivates the need to develop parameter-free algorithms. All right, so let's move ahead. So now let's talk about optimism. So we have already seen in the previous, in the first motivating example that we gave that there might be two scenarios, one without the optimism and the second would be with optimism, where we are seeking hints for the future. Let's try to see this in the perspective of our running example of making policies for COVID pandemic. Now, there is the one way of making policy would be to completely ignore any information that you get from the experts, right? But the second way of doing that would be you have all the historical data, but you also ask few experts about their opinion without making a decision, before making a decision, right? So you say that based on the report so far, in the next round, we should ease the mask mandate. And some expert might come to you and they might tell you that, yes, that should be fine for next month. So you are trying to get some hint about the future from some expert, right? So we may have some information about the future and we can use that information as hints in our algorithm. We can incorporate that information in our algorithm, and this is called optimism in online convex optimization. So why is the problem of online convex optimization challenging? The main reason being we are taking decisions before we observe the loss, before we observe the feedback. So adversary might make our life very difficult in this scenario, right? So this is the setup that we have already seen. Now, if you have access to some hints about the future, so you already have some information about the future, then if you incorporate that information in your algorithm, then regret bound might improve. Like that's the hope. So this is called optimism, and we can incorporate this optimism in our, say, online gradient descent sort of update. So we do updates in 2 steps. So we make an intermediate step, and this decision would depend on the gradient information, the feedback that we received. And then we make the final decision, and this final decision will also take into the consideration of the hint that we are receiving, right? So this MT plus 1 is a hint about the future, and we use that information to take the final decision. And optimism works pretty well. So if you choose the learning rate eta t carefully, then you can manage this order of d and square root of 1 plus summation across t is equal to 1 to capital T, the norm of difference of the gradient and the hint square, right? So it's obvious that if MT is close to this gradient information, so if your hints are good, they predict the future in an accurate manner, then this would lead to good performance, right? If they are bad, then you'll end up, and if they are bad and this norm of the gradient is bounded, then you end up with order of a square root of t sort of regret bound. Optimism actually works well in online convex optimization setup. But now the question is, what is a good choice for hint? So again, let's go back to the very first example that we discussed, where I asked you whether I should keep an umbrella for next day or not, and you said that there is no need because it did not rain today, so it might not rain tomorrow. So taking that idea, if you don't know anything about the future, then it might be a good idea to keep the hint as the current round's feedback. So you already know what is happening today, and you just assume that the same thing would happen tomorrow. So you use that information about today as your hint for the tomorrow. So you take MT plus 1 as same as this gradient information of FT theta t. And this works well when functions are not changing too much. So this is the idea of taking hint when you don't know anything about the future. Right. So now I talked about optimism. I talked about why do we need these parameter-free algorithms. So let's talk about some existing results in this area. Remember the definition of regret. We have already defined this. And now we are saying that can we come up with more adaptive algorithm? And the answer is yes. The first thing that we can do is we can remove the dependency on the domain diameter capital D. So the regret bounds that you see in this slide, they don't depend on the diameter information capital D. Rather than that, they depend on the information about the baseline. So U is the baseline that you pick, and regret bounds depend on the information about U, so norm of U. The second thing that you can do is you can have adaptive bounds even when you don't know D and you don't have any, say, bound on the norm of the gradient. So the first scenario is D is not known, diameter is not known, but you at least have this bound on the norm of the gradient known to you. Then you can come up with some adaptive regret bounds. In the cases when even that is not known, so if even the diameter information and the information about bound on the norm both are unknown, then also you can come up with some good regret bound which only depends on norm of U and not D. So these are existing results, and they work pretty well. So now we talked about different frameworks, and there are some existing results. Now we'll talk about something where there are no existing results. So the main contribution of our work, this work, would be in this framework. So we already discussed some questions related to this, where we are saying that what if the feedback is not adversarial, right? So the feedback that you're getting from the environment, it might not be adversarial all the time. So can we go beyond worst case? Again, let's come back to our running example of COVID pandemic, and we are trying to make policies for this, right? Now think about this situation, that you are in California and you want to decide whether masks should be mandatory in California in February of 2022. And the feedback that you receive in this month, February of 2022, by conducting a survey in California tells you that it's a good decision. Having mask mandate is a good decision. Now, if another group conducts the survey at the same place with the same people, then chances are they might also come up with the same conclusion that yes, it's a good decision, right? Now, you can measure this goodness of the decision from a scale from 1 to 10. So you might say that it's a good decision with rating 8. The other party might say that it's a good decision with rating 8.5 or 7.5. So there might be a small variation, but both of you might agree that this is good decision. So this is kind of saying that, so there is a distribution and you're taking your feedback from distribution. And there is an expected value for this distribution, but there might be some variance, right? So this is, things are not completely adversarial. So within the round, we are saying that you are picking your feedback from a distribution with maybe some variation. There might be some other scenario as well. So now you conduct this survey in, say, February of 2022, same place, same people, and you come up with this feedback that it's a good decision. But if you conducted the same survey 1 year back, so in February of 2021, then you might say that this decision is bad. So now across the round, there is also some variations. So there are two sort of variation. One is within the round, there are some variation, and there is across the round, there are some variation. Now the question is, can you model these variations in some way? And this is what we'll try to do next. So we just saw this, that there might be variations within a round and there might be variations across the round, and we want to model this variation. This shows this pictorially. So you need to pick convex function in all the rounds, right? So in the round T, say you take this convex function, which looks like this square loss. You have this expected loss function, which is shown in this solid pink line, but there might be some variation which are shown in these blue lines. If you go across the rounds, then you might not get the same quadratic loss function. You might get a linear loss function, which is still convex. Again, this linear loss function will have this property that it has an expected value, but there might be some variation. So there are some variation within the rounds and there are some variation across the round. So we want to model these type of variations, and the modeling technique is what is called stochastically extended adversarial model. Right, so we'll define two parameters here. One is this small sigma square 1 to t, which we'll call cumulative stochastic variance. It measures the variation within the round. So if you see this gradient of small ft theta, this is the feedback that you are getting, and we are trying to measure the variance of this quantity from its expected value, which I denote with the capital ft theta, right? So we define this quantity to across all the rounds, all the capital T rounds, to somehow collect all the variation within the rounds. We can define this another quantity which captures the variation across the round, and we are calling it cumulative adversarial variance, and we are denoting it as capital sigma square 1 to t. So this captures variation across the round. So you see that we use ft here and we use ft minus 1 here in this definition. So again, once again, to capture variation within the round, we are using small sigma, and for capturing variance across the round, we are using capital sigma. So let's talk about the stochastic case. In the stochastic case, you are getting a feedback from a distribution, same fixed distribution across all the rounds. So at round equal to t, round equal to t plus 1, you are picking your feedback from the same distribution. So that's the stochastic case. In this case, the adversarial variation is 0 because expected loss function is same for all the round. Now, in the other extreme would be the completely adversarial case, where you are using adversarial loss sequence at each round. So you are putting, you can assume it like saying that the distribution is Dirac delta distribution on a very particular function at each round. So there is no variation in picking the function within the round, but there is variation when you pick the function across the round. So small sigma is 0, but capital sigma is non-zero. And this framework, which is stochastically extended adversarial framework, this covers everything in between. So it covers the completely stochastic case and completely adversarial case and a mixture of these two scenarios. So we want to have good regret bounds in these setup, this stochastically extended adversarial setup. That's our contribution in this paper. So right, so what is the big question here? So can we still control the expected regret in this stochastically extended adversarial or SEA model, right? Two requirements. the regret should be adaptive to variations. So regret should be small. When you have small variation, if both capital sigma and small sigma are small, then you should have a small regret. And regret should only grow as order of square root of t. That is the worst case regret, when the small sigma and capital sigma become large. That's the requirement that we have, and we want to answer this question. Is there any question so far?
None. So the first one, the regret should be small. Again, the when variations are these are small. Again,
Yeah.
this is part of the setup, right? So this is something we assume.
No, this is something we expect, that if variations are not too much across the round, then we should be able to do better. So this is somewhat saying that adversary is picking just one single distribution and picking loss from there, for example, and this distribution is easy to learn, for example.
Okay. And adversary also does not have knowledge about future, right? So
Adversary does not have knowledge about future, but adversary knows your past decisions, and in fact
okay.
the decision for that particular round as well.
Okay.
Yeah.
Okay. So fine. Well, I have a separate question, but I'll ask at the end. Yeah. Yeah.
Okay. Yeah. So right. So far we have been trying to establish the setup or framework that we are working in. Next, I'll show some results and show some algorithm that we are using to get those results. Now it will get a little bit dense in terms of math, but again, I'll ask you to focus on the big ideas. The math will follow anyways. Right. So the algorithm that we went ahead with is called optimistic online Newton step algorithm. So this is, so if you know about on Newton step algorithm, then you might know that this is a second order algorithm. So it also needs information about Hessian. So in that sense, we are making second order updates, but since we don't have any information about Hessian of the loss functions, we are trying to mimic the Hessian. So we are sort of making pseudo second order update. The exact update rules are not important, and the quantities that you see in this slide, how we get these quantities, that's basic. So these quantities are coming from the analysis of the algorithm. And I won't spend too much time on those quantities, but I'll tell you what is important to note here. So one thing important to note here is this is an optimistic algorithm. So you see the first step, it uses the hint, and you see the last step, it uses the effective gradient information that we have in the problem. So this is an optimistic algorithm that we came up with. The second thing would be, you see there is this requirement in the third line where we are saying that if you take the difference of the gradient and the hint and you take the norm, that is bounded by some quantity zt. And to run this algorithm, we need information about this quantity zt. So that is the second important part, that we need to know this bound when we run this algorithm. Now this is tricky, right? Because if you don't have any information about the feedback, then how would you know this bound? And we'll discuss this in more detail in next few slides. Other than that, how the quantities look like, that's not very important at this point of time. So let's talk about this in a little bit more detail. So let's take a simpler case. Let's take the case when we have access to the diameter information, and we also have access to the bound on the norm of the gradient, which is g, right? So how do you pick hint in this case? We have already discussed that. We'll just take the information from the previous round. So we'll pick mt to be gradient of ft minus 1 at theta t minus 1. The parameters in this algorithm, they involve diameter d and this bound on the norm g. And it must be known to run the algorithm. So zt, if you again remember this zt, this is the upper bound on this gradient and the hint. We can just pick it to be 2 times g. Since we know g, we can always pick it to be 2 times g. This is the simpler case when we have all the information about d and g both. Then we can pick this particular learning rate. Again, don't worry too much about the exact expression for this learning rate. It comes from the analysis, but we can pick this learning rate with the information that we have seen so far in our algorithm. Now, how does optimism help us to get results for a CS setup? It is coming due to this particular inequality, and this you will have to prove this inequality, but for now you can just take it as it is. So if you see this difference between gradient and hint, you take the norm square, you take this sum across all the round, then this is bounded by this quantity in the right hand side. And you can already see that it contains two quantities here, right? So you have your focus on second quantity and the third quantity. So the second quantity, after taking expectation and supremum and everything, this will give you capital sigma, and the third quantity would give you small sigma after taking the expectation and everything. Now there are other quantities that you need to deal with, but you can still see that once you have the optimism and once you pick empty to be this gradient information of the previous round, then you already can see how it leads to some good result in SEA setup. We won't go into the detailed proofs. So you just know for now that this inequality would help us get good results in SEA setup once we have the optimism in the algorithm. And indeed it does. So you can prove that this optimistic online Newton step algorithm would give you expected regret, which would only depend on small sigma and capital sigma. In the worst case, it's still order square of t, but if these are small sigma and capital sigma are small, then this regret would be really good. This is the case when we had known both diameter and the bound on the norm. I'll make another remark that you don't need this particular algorithm that we have. So this online Newton step algorithm is not needed to get this guarantee. You can get this guarantee by just using online gradient descent as well, if you know the diameter and G both. The interesting parts are what happens if you don't know anything about the diameter, and what happens if you don't know anything about the diameter and the bound on the norm both. And we'll see those scenarios now. Before that, I'll just talk about this meta algorithm, which is how do you use experts to make better decisions in this framework. I'll have to spend some time on this because we'll be using this meta algorithm later on. And this meta algorithm is a complicated beast, but I'll tell you what is the property that it has. So it has very complicated structure, but we won't go into the complicated structure. We'll focus on the properties that it has. So here is the idea here. Suppose you don't know how to take a good decision on a particular round, right? Particular round T. So what you do is you employ capital N number of experts, and these experts would give you some suggestion. So expert number 1 would tell you that you play theta T1. Expert number 2 will tell you that you play theta T2. Similarly, expert number capital N would tell you that you play theta Tn, right? Now you feed all these suggestions into this meta algorithm. What this meta algorithm does is it gives you a probability distribution across all these decisions. So this WT is coming from this N simplex, and the final decision that you take is a convex combination of all these suggested decisions by the expert. So you play this theta T in the round, and that is a convex combination of all the suggested decision by the expert. So we use this meta algorithm to combine many of the experts expert decision. We can also call them base learners. Now it has some good properties. One of the good properties that it has that it is adaptive to multiple scales. What is the meaning of that? The meaning of that is if each of the expert is playing in a say different domain. So if the diameter size for each of the expert is different, then the loss that they'll see the loss would have different scale for different experts. And this meta algorithm that we are using and we'll use in future would be adaptive to those multiple scales, right? The second important property it has, it leads to good regret bound. So what is the meaning of good regret bound? The meaning of good regret bound is if you compare your decision, that is theta T, so ft theta T, with a decision by one single expert J. So say ft theta T J, and we'll call this difference a meta regret. So basically you're comparing your decision with a particular expert J, then that is a manageable quantity which only depends on the parameter of that Jth expert. Now this seems like an easy thing to prove, but it actually requires some work to prove that this actually happens. Those who actually know something about the convex function, they'll quickly see that ft theta T, you can write this as ft and then this convex combination of all the decisions, and using the convexity property, it just is upper bounded by this summation across j is equal to 1 to capital N W Tj ft theta Tj, right? And you can model this as this inner product. And the loss by one expert, you can also model that by this inner product, and then you can try to bound this quantity, the one in the middle in the last line. But for now, we'll just assume that we can combine the decision from the base learners without worrying about their scales. And the second is it leads to some manageable regret bound. So this bound by the meta algorithm would be manageable to us. So how does this help? It helps in this scenario when D is not known. So now we are getting into some complicated scenario. So what if diameter is not known to you? Now we already have one algorithm which works when diameter and this bound on the gradient norm both are known. So we'll use that algorithm as building block. So we'll use this optimistic online Newton step as building block. So each of the expert would be playing the same optimistic online Newton step that we have seen previously, but they'll be playing it in different domains. So expert number 1 will be playing in domain D1, expert number 2 will be playing in domain D2, and so on and so forth. They'll be making some suggestion about decision at round T, and we'll combine these different suggestions using this meta algorithm that we already have with some good, nice properties. And we'll take the convex combination of the suggestion and we'll play that as our final decision at round T. What are some of the properties of this guy? So we'll be employing log capital T number of expert. So the total number of expert that we'll be employing would be log of capital T. Now I told you that each expert is playing the game in a different domain. So the DJ for each expert, say for example, jth expert would be 2 to the power j. Now you see this third point, which is the decomposition of regret, and this decomposition works for any j that you pick. So the choice of j resides with you. So this decomposition works with any j that you pick. So you can see that this regret can be written in two parts. One is the meta regret, which is the comparison of your decision with the decision of this jth expert, and we already saw that this is manageable quantity. This is one of the property of our meta algorithm. The second part, if you see, this is basically the game played by this jth expert, right? This jth expert has a bounded domain DJ, which is known to us, and they are running this ONS algorithm in their own domain. So we already know how to bound this second quantity. We already know how to bound the ONS regret quantity. So if you combine these two regret bound, then you should get a regret bound which is manageable. Now there are some questions yet to be answered. The first question would be which expert would you pick? So we'll pick the expert. So we'll pick the smallest j, the j expert, such that this norm of u is less than dj. Remember that this you don't have to do this while running the algorithm. You only do this while analyzing the algorithm. So you can always pick any j that you want. So we will pick smallest j such that this norm of u is less than dj. And by our choice of dj, so basically we are doubling dj for each expert, right? So once you pick your norm of u like this, then you get this inequality naturally, where dj would be less than equal to 2 times norm of u. Why is this important, or why is this useful? So when you talk about this regret bound for the second part, right, ONS regret bound for this expert j, then this regret bound would depend on the diameter for that particular expert j. And this diameter would be dj, but the overall guarantee that we want to give, we don't want the overall guarantee to depend on the diameter information whatsoever. So this bound, the lower bound and the upper bound, would make sure that any occurrence of dj, we can replace that by norm of u of norm of 2u, whichever side works. So this, by carefully picking this expert, we can have a bound which only depends on this norm of u and not the domain of the expert. And the meta regret is controllable using meta algorithm anyway. Here there is one small assumption. I'm assuming that this norm of u is less than equal to the maximum diameter side, right? So I can only pick this expert if this norm of u resides within the maximum diameter of the expert. So this norm of u should be less than equal to d max. That is possible. But there is always this case, which is what happens when norm of u gets bigger than the maximum diameter that we are considering, and that can be handled as well. So if this norm of u goes more than the maximum diameter that you are considering, then we'll just use this trivial decomposition, which comes from convexity, and then you can use Cauchy-Schwarz inequality to get this bound 2 times g times capital T and norm of u. Now here is the trick. So since we are picking log t number of experts, so the diameter size, which is 2 to the power n, is nothing but capital T. So by this inequality, so since norm of u is greater than equal to maximum diameter, we can show that this norm of u is greater than equal to t. So the bound here that you're getting 2g times capital T times norm of u, you can replace this t by u. So the bound, the eventual bound that you get would only depend on norm of u square. It won't have any quantity such as capital T. So this way we can handle all the cases, and overall, if you combine this everything in one derivation, then you'll get this expected regret bound, which only depends on norm of u. It does not depend on the diameter information, and depends on the quantity small sigma and capital sigma. Going from optimistic result to ACA result, I told you that we already have an inequality to deal with those sort of scenario in the analysis. All right. So this is the case when D was not known to you, and we ended up having some regret, which only depends on norm of u and small sigma and capital sigma. Now, the most challenging scenario when both diameter information and the bound on the norm are not known. This is indeed a challenging task. Recall that if you want to run our algorithm that we propose, then you need to know zt and the diameter d at any round t minus 1, right? And we don't have both the information in this particular case. So the idea here is we won't use the gradient information that we are receiving, but we'll rather use a truncated gradient. And this truncated gradient has the structure like whatever is shown in the slide, where we define BT to be this maximum of maximum of the quantity, which is the difference of gradient and the hint, the norm of that, from 0 to small t, right? So at round t, we don't know b of t, but we know b of t minus 1. But the way we are constructing this gt tilde, which is the truncated gradient, if you compute this gt tilde minus mt and take the norm, if you compute the bound on that, then you'll end up with this bt minus 1 quantity, which is known to us at round t. So we'll just use that bt minus 1 as our zt in the algorithm, which we need while running the algorithm, right? Of course, when you do this truncation, you lose something. So you'll have to deal with those extra terms, and we do that in the paper. But this is the main idea here. But it doesn't stop here. So now we have dealt with not knowing zt, but we still don't know the diameter d. So we'll start with some diameter that we think should be okay. So we start with a constant diameter d1, but this may not be large enough. So what we'll do is we'll use something called doubling trick to deal with this unknown diameter d. So what we do here essentially is we start playing the game assuming that there is some diameter that is valid. So you play theta t, you receive the feedback, you construct this truncated gradient, and you run our ONS that we have already seen works when you have information about the diameter and the gradient bound. So this will work, but there might be the case that this diameter that you have picked might not be big enough. So if this diameter goes below certain quantity, then you just double it and you restart this entire game. So you need a lot of restarting in this setup. Anytime you detect that diameter is not big enough, then you just double the diameter. So the question is, how many restart would we need at max? You can see that the diameter would never go beyond square root of t, order of square root of t, because of the way we are doubling this. So so the maximum, since the max diameter limit is limited by order of square root of t, so the maximum number of restarts you will need is log of capital T. So not too many restart, right? The second thing that you would notice is that for each unique choice of diameter, you'll determine an interval. Meaning you start playing the game. So starting from the round 1, 2, 3, 4 up until a certain duration, you will have one diameter d1, and then after some time you double it, so you'll have another diameter d2 for some round. So each unique choice of diameter would determine an interval for you. So at each interval, you are playing with a unique choice of d1. So at interval 2, after restart, you change your diameter to d2. And at each round, you are running ONS, right? The Newton step algorithm that we have seen already. By the way we are constructing this diameter, we know that there might be at max log capital T restarts. Now, one extra thing that we'll do in the analysis, this is not needed while running the algorithm, is we'll change the comparator for each interval, and we'll pick this comparator UT in this particular way. This basically implies that for any round, either UT would be equal to U, or we'll acknowledge that our diameter is smaller than norm of U. only two possibilities is possible. Don't worry too much about math again. The idea is that we are dividing everything into different intervals, and we have different comparator for different intervals. If you do that, then you can again decompose your regret formulation into two parts. The one part would be this ONS regret in each interval. Since you have m such interval, you have m times ONS regret, and you know how to handle it because you have diameter information for each interval. But you need to deal with this extra regret information that comes because you're changing the comparator at each round. You can show that this extra regret remains small. There are two observations that you can use in that. One thing would be this ut minus u quantity after using Cauchy-Schwarz would be bounded by 2 times norm of u, because you can always show that this norm of u2 is less than equal to norm of u by your choice of ut. Second would be you still need to deal with this sum of gradient information, and by the choice of our diameter, we know that this sum of gradient information is related to dt, which in turn is related to norm of u. So if you do some manipulation, algebraic manipulation, you can show that this extra regret is not too bad. And once you add everything up and make that jump from optimism to SEA framework, you'll get a completely parameter-free algorithm in SEA framework. And overall regret bound in this case would be whatever is shown in the slide, which only depends on norm of u or small sigma and capital sigma. There are few open questions. So this is a very first work in this sort of setup. So people knew about SEA framework, but they did not have any completely parameter-free algorithm in SEA framework. So these are very novel result in this framework. There are some open questions though. In the last scenario, we are restarting our algorithm over and over again. In practice, that's not recommended. So can we avoid these restarts when both D and G are not known? We don't have any answer for that. Now, the second thing would be if you see this leading norm of u square scaling of this square root of term, right? So this is not the ideal scaling. We don't know whether it's tight or not, but we expect it to be norm of u, not norm of u square. That is the expected dependency, although we don't have any proof for that. So can we change that u square, norm of u square to norm of u? We don't know that yet. Third one is, can we consider other feedback models? So I told you that we are considering first order information as our feedback. Can we try other feedback models? For example, can we just say that the feedback that we are getting is just the function value, not the gradient? It's called bandit feedback, and can we have some results for that bandit feedback model? And we actually have some work here. We actually have some results in this bandit feedback model now. When we wrote this paper, during that time, we did not have any result. So these are some open directions. And yeah, so I'll stop my talk here. I think I managed my time well, I believe. Yeah. So if there are any questions, then we can discuss that. And these are my contact information. Thank you for your attention.